All right, so this is section 4.2, number 12. I think we started this one the other day, but we didn't finish it.
Number 12 is x plus 2y. 2x plus y for that first.
Yeah,
It is. So I copied half of number 11 and half of number 12.
you can't do that.
Yeah, when you do that, you don't usually get the right answer. Is that better? All right, so we started this one the other day, but we didn't finish it, and I think it would just be best to start right over from the beginning. All right, so what we're going to do, we're going to take the Laplace transform of both sides. So we're going to have the Laplace transform of x prime equals the Laplace transform of x plus 2y. We had a rule for the Laplace transform of x prime. What's our rule for the Laplace transform of x prime?
S times big X to the S.
S times big X to the S minus
X0.
x of 0. On the right-hand side,
Big X represents just what?
big X is the Laplace transform of little x. So on the right-hand side, we'll see the Laplace transform of little x. Big X plus 2, what's the Laplace transform of little y? Big Y. All right, so there's what happens to the first equation when you hit it with the Laplace transform. Exact same thing for the second equation. I'm going to take the Laplace transform of y prime equals the Laplace transform of x plus e to the negative t. Oh, and I should have done this too. What's this x at 0? 0, that was our initial condition. So that part really just drops out. Okay, what's the...
Wait, is that big Y or little Y?
That's a little y, sorry.
Above the 2Y and S, is that little Y or big Y?
This is a big Y. That's a big Y. The Laplace transform of little y is big Y. What's the Laplace transform of little y prime? S big Y minus y at 0 equals, over here, the Laplace transform of little x, big X, plus the Laplace transform of e to the negative t. Get out my magic sheet of Laplace transforms. The Laplace transform of e to the negative t is 1 over s plus 1, because it would be 1 over s minus negative 1. Over s plus 1. And once again, our initial condition gives us that y at 0 is 0, so that part drops out. What we want to do now, we want to take these two equations that we have. We want to get all the things that have big X and big Y together on one side, all the things that don't have big X and big Y, put them on the other side. In other words, I'm going to move this X of Y, I'm going to move this big X over, and I'm going to move that 2Y over. So it gives me S, X at S, minus X at S, minus 2Y at S, equals 0. And even that I'm going to rewrite. What can I do with those first two terms?
X of S times.
I can factor out an x of s. So I'm going to write this equation as s minus 1 times big X minus 2 big Y equals 0. And then the second equation, I'm going to subtract the big X. So I'm going to have minus big X plus s y at s equals 1 over s plus 1. What this gives us now is this gives us a system of equations. We had a system of equations to begin with. what's the difference between this system of equations and our new system of equations? We've done Laplace transforms. In a sense, this original system of equations had how many variables in it?
15 billion.
Well, I don't know that's 15 billion, but there was x,
Yeah.
there was y,
T.
there was derivative of x, derivative of y, and then the letter t. So there were a lot of variables. How many variables do we have in this new system of equations? We have x, we have y, and s. And our goal here is to get big X equals something with the letter S in it. And then we can do an inverse Laplace transform. Get big Y to equal something with the letter S in it, and then we can do an inverse Laplace transform. So in essence, what we've done is we started with an equation that, in a sense, had 5 variables. We've reduced it to a system that only has 3. 3 is less than 5, so that's better, right? So far. All right, now the deal is,
Yeah.
how do I take this system of equations and get, for example, maybe y all by itself? Well, you could use techniques that you learned in previous algebra courses. What I mean by that is you could take this first equation, multiply everything by s, take this second equation, multiply everything by 2, and then add the equations together. The y's would drop out and you would only have x's left. But that gets pretty ugly when you're dealing with letters. Multiplying by s where you already have an s in it gets pretty ugly. The standard way to solve these is to use Cramer's rule. All right, so how did Cramer's rule work? We create a matrix D which has the coefficients. What are the coefficients in this case? Not just one, s minus 1. The coefficients in this case have letters in it. They're not just numbers. So we have s minus 1, negative 2, negative 1, and s. Remember, the D matrix is just the numbers. In this case, the numbers have some letters in them on the left-hand side of the system. Next, we create the matrix D sub x. And how did D sub x work again? I take these answers, which are 0 and 1 over s plus 1, and I plug those in where the x's are. The x's are in the left-hand column. So I'm going to have a 0 and a 1 over s plus 1. And then I recopy whatever I had from D before. So I'm going to have a negative 2 and an s. And finally, I do the same thing for D sub y. The difference is D sub y, these answers go in the y spot, so I'm going to have a 0 here and a 1 over s plus 1. And then I go back to my D matrix. So I'm going to have an s minus 1 and a minus 1. Almost where we need to be now. Capital X is going to be the determinant of the D matrix, the determinant of the dx matrix. What's the determinant of the dx matrix? Well, I multiply this way, I get 0. I multiply that way, I get. But remember, it's 0 and then minus when I multiply that way. So I have a negative already, and another negative is going to make that positive. So that's 2 over s plus 1 divided by the determinant of this D matrix. So I multiply this way. That's s squared minus s. Multiply that way. Minus 2. Again, remember we subtract. Negative 1 times 2 is 2, but then it's a subtraction. Okay, so this is S squared minus S minus 2 factors. How can you factor S squared minus S minus 2? S plus 1, S minus 2. But I already have this thing up on top. So I'm going to end up with 2 over S plus 1 squared times S minus 2. All right, let's do the same thing for the big Y. We'll get the big Y all by itself too. So big Y is the determinant of the dy matrix. So I multiply this way. That's S minus 1 over S plus 1. And then I divide by the determinant of the D matrix. The good news is I already figured out the determinant of the D matrix. It's S plus 1 times S minus 2. I don't need to go through all that work again. All right, so big Y is S minus 1 over S plus 1 squared times S minus 2. Questions so far?
Will it always work out so that the X and big Y have the same denominator?
Will it always work out so that big X and big Y have the same denominator?
That is always
Hopefully. I think the answer is yes.
They're always divided by D, but I wasn't sure if they cancel really sometimes.
Right, they're always both divided by D, so they're both going to start out similar.
Right.
The question is, will you end up having the same thing on bottom here? And I think the answer is yes, because where's this bottom coming from? This bottom came from this part of it, didn't it? That's where the 1 over S plus 1 came from. And so when you plug this in, you're going to plug it in once for the dx matrix, and that's where that came from. And you plug it in once for the y matrix, and that's where that came from. So yes, I do think the x and the y will always end up having the same denominator.
You can check yourself like
So you can kind of check yourself like that. All right, well, we're almost done.
Oh boy.
Oh boy, what do I mean almost done?
Time to do an integration of parts.
We started with little x and little y. Still can't see it, way up there, little x and little y. When we get all done, we should have little x equals and little y equals. So we need to find the inverse Laplace transforms of both of these. And so I agree completely that we need to do partial fractions. All right, so capital X of S turned out to be 2 over S plus 1 squared times S minus 2. How do you split that up using partial fractions?
You have 3.
X plus B over
A over S plus 1.
And then another B over S plus 1. And then C over S minus 2.
Close. B over S plus 1 squared.
Oh, jeez. Yeah.
And a C over S minus 2. Okay? So you recognize the difference. This is S plus 1 is linear. So we have S plus 1 squared. We have a repeated linear. That's different from having S squared plus 1 on bottom. If I had S squared plus 1 on bottom, that would be a quadratic. So then I would need an AS plus B up on top. I would need a linear. Okay, we clear our fractions. We get 2 equals A times S plus 1 times S minus 2. plus B times S minus 2 plus C times S plus 1 squared. Never mind. Pick your favorite number in the world for S. 2 is a great number. 2 equals, when I plug 2 in, I get 0 here, so this whole piece is gone. When I plug 2 in, I get 0 here, that whole piece is gone. 2 plus 1 is 3, 3 squared is 9, so I get 9C. So C is 2/9. When I plugged 2 in, I got 0 right there, so the whole thing was 0. A disappeared. B disappeared. That's why I liked the number 2 so much. What other number do I like a lot? Negative 1, because when I plug negative 1 in, I get 2 equals. This is 0, so the A disappears. This is 0, so the C disappears. I get negative 3B. So B is negative 2/3. Now what about A? I know what B and C are, so I can plug in B and C.
A is 0.
I hope so, but I don't think so. I'm going to plug in my number for B, I'm going to plug in my number for C, and I'm going to pick another nice number that I like for S. The only rule is I can't use 2, I can't use negative 1. 0 would be the number I would pick. 1 would work just as well, but I like 0 better. It's easier to plug in 0. S equals 0. So when I plug in S equals 0, I get 2 equals. Let's see, I plug in 0, I'm going to have 1 there and negative 2, so that's negative 2A. Plus, B is negative 2/3. And I plug in a 0 there, I'm going to get a negative 2. So negative 2/3 times negative 2 is 4/3. Plus, C is 2/9. I plug in 0 there, 0 plus 1 is 1, 1 squared is 1, so that's 2/9. Oops, 2/9. What's 4/3 plus 2/9? 14/9. What's 2 minus 14/9? 4/9. So 4/9 equals negative 2A. A is negative 2/9. Okay. Little x of t. Here's the answer I want. Little x of t is the inverse Laplace transform of negative 2/9 over s plus 1 minus 2/3 over s plus 1 squared plus 2/9 over s minus 2. Now I need to take the inverse Laplace transform, so I go to my big sheet of inverse Laplace transforms here. What do I do when I have an s plus 1 down on bottom? It's the same as s minus negative 1, so that's going to be e to the negative t. So that one's negative 2/9 e to the negative t. Minus 2/3. Do you see one that has an s plus 1 squared down on bottom? Right here, s minus negative 1 squared. So that one's got a t, e to the negative t. And then finally, plus 2/9 e to the positive 2t. Because you have s minus 2, a is the number 2.
S, right?
Now we have to do the exact same thing for the letter y. We're still only half done.
Oh, no.
We got x. Now we got to find y. Well, we're more than half done. But we need to go through the same process for capital Y. Remember, capital Y was... the heck was capital Y? S minus 1 over that same denominator. S plus 1 squared times s minus 2. Exact same partial fraction decomposition, a over s plus 1, b over s plus 1 squared, c over s minus 2. Wipe out the fractions again. S minus 1 is a times s plus 1 times s minus 2 plus b times s minus 2 plus c times s plus 1 squared. Start plugging in your favorite numbers again.
Actually, when you're clearing the fractions, you're multiplying both sides by the denominators of the a, b, and c, right?
That's exactly right. I'm multiplying by the common denominator, which is that.
Oh, I see. Yeah.
So, for example, this s minus 2 cancels with that s minus 2, which is why I have the s plus 1 squared left over. So on and so forth.
Well, s equals 2.
How about s equals 2? I get 1 equals. A would disappear, b would disappear, c times 9. So c is 1/9. What's that? Not quite the same thing. Because back up here we had just the number 2 on the left-hand side. Over here we have s minus 1. So what's going to happen is we're going to get the same denominators, but we're going to end up with different numerators. Here we had 1/9. Back up there we had 2/9. Plugging in s equals 2. No, s equals -1. We already did s equals 2. When I plug in -1, -1 minus 1 is -2. Equals. The a disappears, the c disappears. -3b. So b is 2/3. Almost the same. We had b equals -2/3 before. And finally, plug in s equals 0, and plug in the b number, and plug in the c number. -1 equals a times -2, that's -2a, minus 4/3, because I get a -2 there, -2 times 2/3 is -4/3, plus 1/9. What's -4/3 plus 1/9? -11/3. So then I have to add 11/3 to both sides. What's 11/3 minus 1? 8/3. And then what's 8/3 divided by -2? -4/3. Ninths? Ah, rats. So that, you're right, that would be -12/9. So that would be -11/9. Then I have to add 11/9 to both sides. That would be 2/9. Better? Alright, so final answer. Little y of t is, I'm going to have the 2/9 inverse Laplace transform with an s plus 1 on bottom. That's an e to the -t. And then my b was 2/3. I look in my chart again. That one's a t e to the -t. And then the c was 1/9. Look in my chart. That one's an e to the 2t.
They're almost identical.
They are almost identical. I agree. In fact, the only thing that differs is the coefficients are the only thing that's different. What's happened? Your equation should look exactly the same, simply different coefficients. Questions?
is really, okay. Yeah. Struggle.
Certainly very long, isn't it? No arguing that.
Did we learn a shortcut?
Not today. When we get to chapter 5, we will we will deal more with systems of equations. There are other techniques that sometimes work, sometimes don't. Sometimes this is the way you have to do it. Other questions?
So is this all over?
We finally finished section 4.2. I think it only took us 3 days. But I think we're finally done it. That was a good one. Other questions?